Hey everyone, welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down, I'll gather them up, and I'll answer them here. Now, once again, I record this show live normally every Monday at 5 p.m. We had to record a day late because of weather. That sounds weird. But if you want to join us live every Monday at 5 p.m. Pacific time on my YouTube channel. All right, let's get into the questions. Matt Lowe, why is iron the largest element produced in a star, and where do all the bigger elements come from? The beginning of the universe, all there was hydrogen. And then for the briefest moment, the entire universe was kind of like the core of a star. And so you had nuclear fusion going on. And some of that hydrogen got turned into helium. And so now we end up with about 75% hydrogen, 25% helium. And then you got small amounts of other heavier elements. And then the universe expanded to the point that the hydrogen was so far apart that it was no longer the interior of a star. And then the material had to come together through gravity to form stars. And then inside those stars like, say, the sun, you've got hydrogen turning into helium inside those stars. And as the star runs out of hydrogen in its core, it'll shift to higher and higher elements on the periodic table. Maybe it'll start creating carbon or silicon. And for the most massive stars, they just walk up the periodic table of elements until they get to iron. And the thing with fusion is that when you combine 4 hydrogen atoms, and through this process you get, turns into helium, there's like a bunch of steps. So it produces gamma radiation. So it is an exothermic reaction. And all of them, like when you fuse helium, it's an exothermic reaction. When you fuse carbon, it releases energy. And all the time, it's actually keeping the star inflated. The energy is pushing out, and the gravity of the star is pulling in, and you get this balance, and so you get the star. And over time, as the star goes up and up and up this periodic table of elements, it reaches iron. And the difference with iron with the rest of the elements in the periodic table is that iron is not exothermic. So that when you fuse iron atoms together, you don't get any energy out. And so this energy, this pressure that was pushing outward on the star suddenly goes away. But you still got all that gravity pulling in on the star. So I just explained the story of all of the elements up the periodic table until you get to iron. And then what happens is when the star turns to iron, when the center, it's not the whole star, just the very center, the part that should have been fusing and producing energy and keeping the star inflated, when that turns to iron, there's no longer energy. And so you've got the inward force of gravity, no outward pressure, and the star collapses in on itself. It implodes and turns into a neutron star or a black hole. But as this material is coming down together, it's essentially mashing with all of this pressure. At the end, it's sort of moving about 70% the speed of light. And it's like this force just pushing it to sort of cram all that matter into this tiny space. And that's how you get a black hole. That's how you get a neutron star. And not all the matter goes into the black hole and the neutron star. A lot of it just bounces out. But that pressure fuses these atoms together to make elements that are higher on the periodic table beyond iron. That's where you get your gold from, your silver, your plutonium, and many of the other heavier elements. And so that's one source of those heavier elements. The other source of the heavier elements is when you get those neutron stars, when they collide with each other, they can form large amounts of these heavier elements. Obviously, maybe they form a black hole. We're not entirely sure. Maybe they just, when they collide, they just break each other apart completely. But you get this merging of these elements, and you get this enormous release of the heaviest elements, the gold, platinum, plutonium, etc. And so that's both why iron is the most you can get in a star, and that's where all of the heavier elements in the universe came from. Sam Hill, Fraser, I have a question for you. When I watch close-up videos of rockets blasting off, it looks like ice is falling off it while lifting off. Is that really what it is? And if so, why? Thanks. Yeah, it is ice that's falling off the outside of the rocket. And I think the best example, the classic example that we've all seen, is the launch of the Saturn V rocket as part of the Apollo missions. You got these incredible film footage close-up shots of the Saturn V taking off, and you can see these chunks of ice falling off the outside of the rocket. So what is this ice? Where did it come from? Rocket fuel in, say, the Saturn V, but say the space shuttle is a much better example. You've got a fuel, a propellant, that is liquid hydrogen and liquid oxygen. And both of those can only be kept liquid at incredibly cold temperatures. So they're under huge pressure, they're very cold temperatures, and they're kept inside the propellant tank of the rocket. And so because they're very cold, and even if they surround them in insulation, that cold temperature is surrounding the tank. And then condensation from the air collects onto the outside of the tank, and because it's so cold, it starts to form ice. And over time, as it takes, they may start fueling the rocket. It has to sit there for hours, perhaps in the moist Florida sun, and collect this ice on the outside. And then when the rocket starts to launch and shake and rattle, then this ice can break off and fall down. So that's why they get it. Bo Danner. Launched from Earth, what is the theoretical limit of the speed a vehicle could achieve using any and every gravity assist possible in our solar system? One of the big discoveries in space navigation was this idea of the gravitational assist. And we've done many videos in the past, but I'll give you sort of the short version, which is that when you fly your spacecraft towards a planet, say when you're launching from Earth and you're flying towards Jupiter, you fall into Jupiter's gravity well. So Jupiter accelerates you as you come towards Jupiter, and then Jupiter slows you down as you're getting away. It's imagine you're sort of going down into Jupiter's gravity well and you're going back up. But Jupiter also has an orbital momentum as it's going around the sun. And so when you approach Jupiter with your spacecraft, if you can get very, very close to Jupiter, you actually, with your spacecraft, can kind of slow down Jupiter. Or what's really happening is that Jupiter is pulling the spacecraft up to its orbital velocity, which is slower than the Earth. I know it's kind of complicated, but essentially you are gaining orbital momentum and you are stealing it from Jupiter. And then you do this flyby and you continue on through space. And what you get is a net benefit. You get an increase in your velocity. And then you can do this again. You can do a flyby past Saturn and get another increase of velocity. And in fact, this is what the Voyager spacecraft did. Voyager did a flyby of Jupiter, got an increase in speed, flew past Saturn, got an increase in velocity. And then Voyager 2 was able to fly past Uranus and Neptune and continue with these gravitational slingshots. So in theory, you could just keep doing this. Each time you go slingshot past one planet, as long as you're close enough, you can steal a little bit of its momentum and just go faster and faster and faster. So what's the limit? Well, there's a couple of practical limits. The first limit is the escape velocity of the solar system. So, which is, depending on where you are and how fast you're going, depends on whether you measure it from the sun, whether you measure it from the Earth. But say if you're in Earth orbit, and you are attempting to then leave Earth orbit and leave the solar system entirely, it's about 17 kilometers per second. So you've already got 30 kilometers per second of velocity because you're joining the Earth around the sun. You need another, say, 17 kilometers per second. And so if you do a couple of flybys and you end up on a speed that's faster than that escape velocity, well, then you just won't be able to come back into the solar system to fly past another object. So the perfect gravitational assist would be to come as absolutely close to Jupiter as you could, like literally skimming the cloud tops. I mean, really going through the center of the planet would be the best, passing right along its center of mass. But then you could theoretically get about an 80 kilometer per second boost as you fly past Jupiter. And so really you don't need to do a bunch of complicated ones around many. You just need to do one really precise flyby past Jupiter to get the maximum speed possible. And then you're going too fast, couldn't do any more flybys. Like unless you lined up, so you did Jupiter, and then you got Saturn, Uranus, and Neptune, and they're all lined up perfectly, then you could probably get even a little bit more of a kick. And then you're out of the solar system and that's it. But it's still like a fraction of the speed of light. It's still going to take you thousands of years, even with that, to get to Alpha Centauri. So it's not enough of an assist. Pontus Ignell. Would it be possible to use a black hole or such to pull something out from within the event horizon of another black hole? No. Even a black hole cannot pull something out of another black hole. The whole point is that The event horizon of a black hole is the point at which you would have to be moving faster than the speed of light to be able to escape. And since nothing can move faster than the speed of light, nothing can pull you out of the black hole. So once you cross the event horizon of a black hole, you are inside that black hole's event horizon and you're never coming out. Even if a supermassive black hole comes really close, even it can't pull you back out of the black hole. You're gone for good. Scurvy Sam, what is the deadliest thing the farthest away from the Earth that can hurt us? The universe is really just trying to kill us all the time, and so it has no shortage of ways to wipe us off the Earth. But I would say the thing that is most likely to harm us, that is also like the farthest away, is going to be a gamma ray burst. And astronomers are fairly sure at this point that a gamma ray burst is a kind of really powerful star that dies and detonates as a supernova, but it's got this incredibly tangled up magnetic field. And so when all of the energy detonates out of the star, it's channeled along these magnetic field lines. And if you happen to have one of these magnetic field lines pointing directly at Earth, then it's like a death beam that can shoot for tens of thousands of light years and cause damage. In fact, if a gamma ray burst went off and was pointed at us pretty much anywhere across the Milky Way, it would be able to strip the atmosphere off of the Earth, which is kind of scary. Now, the gamma ray bursts that we see are in other galaxies. We see them very far away, tens of millions of light years away. But to have one, or even like billions of light years away. But if we have one go off in the Milky Way and it happened to be pointed at us, it would be a very bad day. So I think that would be the worst. But astronomers have looked, they haven't been able to find a single star that has the potential to become a gamma ray burst that is directed towards us. So we're safe. Don't worry about it. But still, that would be the thing. Arjun, if Blue Origin builds Orbital Reef, would NASA be allowed to rent space? Yeah, I think so. I mean, NASA has shown that it is looking to partner with commercial providers all the time. I mean, with Crew Dragon and the Starliner, NASA did not pay them to build these spacecraft. NASA paid them for seats on these spacecraft. And then SpaceX owns the Crew Dragon. They build them, they can use them for tourist flights, they can use them for servicing space stations, and NASA pays to fly their astronauts to the International Space Station. And in fact, today, we heard that the Russians are planning to send cosmonauts on board Crew Dragon. So you've got more customers for Crew Dragon. And so if another space station was built, and say they actually built this Orbital Reef and they would offer out space for people to rent and people to use, yeah, I think NASA would absolutely spend some money to be able to run some of their experiments. I think like NASA doesn't design and build their own cars, except for maybe lunar rovers. They don't design and build their own airplanes to fly. They take commercial airlines. And so I think NASA's place is to live in the spot where nobody is willing to invest money. And that's the kinds of propulsion, air technologies, space flight, things like that. But if Blue Origin is willing to build a space station and rent it out, yeah, NASA would be one of their top customers. Just like NASA is SpaceX's top customer. More questions in a second, but first I'd like to thank our patrons. Greg Amelia, Paul Kaup, Bill Hamilton, Jorn Albert, Truck Captain Stumpy, and the rest of our 802 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Vanjay Brunazzo, if there was another civilization like ours in another galaxy, would our current technology be enough to detect and communicate with each other? Absolutely. If there was another civilization, even about as advanced as ours, and they had radio, the ability to send radio signals at a coherent, using like a radio dish, like the Green Bank or the Arecibo or the Chinese Fast Telescope, and you could send and receive messages across fairly vast distances if you know where somebody is and you know how you're planning to communicate with them. So up until this point, when we talk about SETI, the search for extraterrestrial intelligence, astronomers have been using their radio telescopes and they've been pointing them at individual stars and listening at various frequencies at these individual stars, hoping that there's a civilization there that is directing a message back towards us. There really aren't any methods right now where we're searching just the sky in general trying to pick up their television broadcasts, because they fall off over time quite quickly. Like, it's almost impossible to detect a signal beyond 10 light years at our current technology. Maybe when the square kilometer array comes out, we could detect signals over 100 light years. But even that is going to be really complicated. And so you really need someone pointing their radio telescope at you, sending off a signal, and you've got to be detecting it. In the past, actually, astronomers have tried sending messages out using Arecibo. They picked a star system that they thought was one that could be habitable and sent a message. We didn't hear anything back, although it takes a long time. So yeah, absolutely. Theoretically, if we received some message from some civilization, we could download the whole message, we could send a response back at them using our radio telescopes and carry out a communication. The challenge, of course, is that you are separated by light years of distance, and so years of time. And so say they're 10 light years away from us, which there's maybe 100 stars within 10 light years of us. Like, maybe they're 100 light years away from us. Now we're into I think 1 million stars within that distance. Or maybe 1,000 light years. Anyway, so we have to wait 100 years for a signal. So we send, hey, how are you doing? And then 100 years later, they get the message. They craft a response. Doing fine. 100 years back for us. It's 200 years for a return message. It's such a great idea. And I actually don't know of a paper. If anybody does know, let me know. But I'd love to read a paper where someone has thought about, like, if we do find an alien civilization, what is the way that we communicate? Do you encapsulate all of humanity into a stream and just send it? Do you be coy about who we are, what we do? Do we wait for them to send useful information to us? It's sort of interesting, almost like game theory, thinking about what would be the way that we would communicate with an alien species on some other world in a way that tries to keep us safe, that tries to learn from them, that tries to share information. Because that's all we'll be able to do. We'll essentially only be able to share knowledge with some other civilization. We learned this math. We developed these kinds of technologies. What have you learned? And then they tell us what they've learned. And then we can sort of fill in the gaps in each other's knowledge. That would be the ideal. Send each other television shows. Anyway, it'd be cool. I'd love to sort of learn more about what people have thought about this idea. Diana Galaxy. Fraser, do you know if things going into a black hole are squished or torn apart? Probably both. So as you fall towards a black hole, the force of gravity on you is different depending on how far away you are from the black hole. So literally, the force you feel on your feet is different from the force you feel on your head as you're getting close enough. And so eventually, those forces are so different that you get torn in half. And then those pieces get torn again, and then those pieces get torn again, just because the amount of gravity is so different. Essentially into the Roche limit. Anyway, the tidal forces of the black hole will tear you apart. And they call this term spaghettification. So you sort of get torn into this long, thin stream of atoms that enters into the black hole. So that's the torn apart part. But then all of your atoms enter into the event horizon and join the black hole, whether it's a singularity or whether it's some larger object inside the event horizon, and you get mashed onto the surface of the black hole. And you are compressed, possibly infinitely. So, we don't really know what's going on inside the event horizon of a black hole. It could be that you just get added to some sphere that's maybe denser than a neutron star. And that I would call being squished, because like a teaspoon of neutron star is millions of tons. Like it's very dense. But maybe it is a true singularity. It's this point in space that is getting smaller and smaller at an accelerating rate, and your material just gets added to it. And that it's like super squished. So both. You both get torn apart and squished. Shadow Mask. Could Starship be used to dismantle and return the ISS to the ground piece by piece? I would think so, theoretically. All of the components of the International Space Station were launched by the Space Shuttle, by various rockets from the US and from Russia. And so they were designed to fit within either the Space Shuttle's main cargo bay or within the fairing size of these various rockets, whether it's a Delta or an Atlas or a Proton rocket. And the fairing size of these rockets is, say, 5 meters across, varying heights. And the fairing of the Starship is going to be, I think, 9 meters across. And so there's tons of room inside Starship to be able to gather up these components. But it would still be tricky. I mean, Starship still hasn't been able to return safely from orbit. I mean, at the time that I'm recording this, we've heard that it may attempt its orbital flight sometime in November. So it could be about a month away from an orbital flight. But this is going to be empty. So it's going to fly to space, it's going to orbit around the Earth, and it's going to try and make a re-entry back through the atmosphere. But if it was gathering up chunks of the International Space Station, then these are going to be adding, in some cases, multiple tons to the weight of Starship as it's coming back through the atmosphere. And we don't know what the aerodynamics of that are going to be, whether it can still make a landing with that kind of weight on board. I'd be interested to find out. But I would say it's theoretically possible that you could do that. Or, say, grab the Hubble Space Telescope. Like, one of the original plans with the Hubble Space Telescope was that the space shuttle would go up to space, grab Hubble, load it back into the cargo bay, fly back down to Earth, then engineers would maintain and upgrade it, and then it would be put onto another space shuttle and launched into space and continue on. And maybe do that for much, much longer. And I think that's still a great idea. It just turned out that the costs of launching on the space shuttle were so expensive that it just didn't make sense. But now the costs on Starship are going to be a fraction of the price of the space shuttle. And it might be that this whole concept of going out, grabbing satellites, bringing them back down to Earth, letting people do maintenance on them, and then launching them again is the way that makes the most sense. So I think you might be onto something. Samurai Hash. Fraser, on the topic of trading information with another civilization, how about sending DNA or their equivalent and creating alien life on Earth, sending our DNA, RNA to them? That is a great idea, and I'm sure it's the source of some science fiction book. I'm sure people in the comments are suggesting it right now. But I like that idea. There was a paper that came out literally today when I'm reporting, and we're probably going to report on this on Universe Today, and they're talking about the fact that humans are not going to be the ones who are going to be making interstellar trips. I mean, science fiction has told us that humans are going to get in their spaceships, they're going to fly to other star systems, but the reality is that keeping a human being alive for those kinds of lengths of time is ludicrous. But if you had other creatures that are tougher, that can handle long voyages, like tardigrades or cyanobacteria, then we could have ways of sending life to other star systems that would require vastly less resources than trying to send a human being. But as you said, the other way is that if you've got some other civilization and they've got the same raw ingredients that we have on Earth, they've got carbon and nitrogen and phosphorus and so on, then theoretically you could send them the plans to print DNA. You could send them the plans to actually construct life forms. Obviously, the more advanced technology would be required, but theoretically you could. And so we could send them ideas of life forms that we've got. They could send us life forms. But there's a million ethical problems. Like, even if you could do this, then you're like, are we going to be letting life forms into our environment here on Earth that are not suitable? They would either die a horrible death under our inhospitable environment, or would run away and outcompete in their natural habitats. You know, we've got invasive species here on Earth. It's always a disaster. And so you can imagine that being an issue. Like, I think I've read a science fiction story in the past about this, just this idea that the way you invade another civilization is you send them, say, information for an artificial intelligence or some biological life form, and you get them to build it. And then it wipes out their civilization and takes over for you. So there would be risks involved. You need to check the code very carefully as you're examining these life forms. But if it was safe, then imagine there was a place where you could go and you could say, these are the life forms that exist on this planet light years away from us. It's a neat idea. Horribly risky idea. Don't do it. Yeah, Jurassic Park. Still busy wondering if you could, but still, I like the idea. Someone should do this as a science fiction book, if they haven't already. I'm sure they have already. Archon Wu. Fraser, what are the chances of the sun killing life on Earth with a solar flare or other solar weather? I would say 0. the chances are absolutely zero that a solar flare off the sun will kill life on Earth. The sun has been around for 4.5 billion years. The Earth has been around. There have been many, many, many flares. I mean, just in our lifetimes, as we've been recording them, we've seen flares over the last, say, couple of 100 years that have been serious, like enough to cause a mega disruption on our technology, to cause auroras to be seen near the equator. Mostly it's our technology is the big risk. And so we know that the sun must have been giving off these flares throughout all of recorded time. And we don't see any evidence in the fossil record, in the geologic record, that there was a time when a deadly solar flare wiped out all life on Earth. There's sort of a range that the sun is capable of producing. The danger of solar flares is really an issue for us from a modern standpoint, that it's electronic equipment that is very hampered by solar flares. And we have become technologically advanced, and suddenly we have stumbled our way into a risk, which is that a big solar flare could ruin our technology and cause our lives a lot of trouble. So no, but solar flares in the past wouldn't have killed all life on Earth, because life is here on Earth, and so it won't happen in the future. Prince Charming. Can two space telescopes be used in tandem to work as an interferometer? Here on Earth, we have interferometers. This is where you have multiple telescopes acting together as a single telescope. The best example of this is the Very Large Telescope, which is located down in Chile. And you've got 4 telescopes as well as a couple of smaller telescopes, and they can, in certain conditions, act as one big telescope. And they mainly do this when they're imaging in the infrared spectrum, because the infrared is more giving. The wavelengths are longer. And so, I mean, if we can do this in Earth, then absolutely we should be able to do this in space, where you don't have gravity, where you don't have other kinds of issues. You can essentially make your spacecraft fly in the perfect configuration to be able to do interferometry. And the cool thing about interferometry, of course, is that when you have 2 telescopes, they act like a telescope the size of the space between the 2 telescopes. But you have to get the telescopes configured so that they are down to within a few hundred nanometers apart if you're going to shoot in the visible. But there was a telescope that was proposed back sort of at the turn of the century, back in the early 2000s, called the Terrestrial Planet Finder. And the plan was to fly up to 4 telescopes in formation, which would be capable of finding Earth-sized worlds orbiting sun-like stars. And eventually NASA decided to cancel the mission, and so they never built it. So still, there has never been an interferometer flying in space. The closest example that's being seriously considered is the European Space Agency's LISA telescope, which is actually going to be a gravitational wave observatory, but it's going to be an interferometer. You're going to have 3 spacecraft flying in a triangle formation. They're going to be holding position very, very carefully, and they're going to act as a interferometer, essentially, to detect these gravitational waves as they pass over top of them. And there's no reason why you couldn't do this, but it just requires flying, this formation flying, which is something that has never been tested in space to that degree. But I'm sure there are missions in the works that are hoping to be able to do that. But we've sort of gone to this point where it makes more sense to do large ground-based observatories. Like, for the longest time, it was space telescopes is what you needed, because you needed to get above the atmosphere of the Earth. But then with the development of adaptive optics and interferometry, you can suddenly build ground-based telescopes that are as if they're flying in space. And on the ground, it's a lot easier to build a much bigger telescope than build something that you would fly in space. And so that's why we're seeing this new round of giant telescopes, the Giant Magellan Telescope, the 30-meter telescope, the extremely large telescope. All of these are 30-meter plus class telescopes with adaptive optic systems on board, and they're going to be capable of imaging Earth-sized worlds orbiting sun-like stars. So the need for an interferometer just hasn't come up yet, but I'm sure there's some in the works, and eventually we will see them fly. All right, thank you everyone for joining me and asking me all of these incredible questions. I really enjoy it. Thanks to everyone who posted your questions in the comments. I get a bunch of them and answer them in the show, but also all the people who join me for the live show. Again, we do this every Monday at 5 p.m. Pacific time. And so you can join and ask your questions live and even have a back and forth conversation with me and other people watching. So come join us sometime. All right, we'll see you next week. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights about the story, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all of my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.